Let's learn how to solve a frame problem like this in ANSYS. So we have a two beam frame. We have one beam here and one beam there. One of the beams has a distributed load applied to it. The other beam is does not have any external forces applied. Beam 1 is at 45 degrees with respect to the global coordinate system, and beam 2 is parallel to the x direction. These are the values that we're going to use. Young's modulus is 210 gigapascals for the entire frame. Poisson ratio is 0.3. L1 is 30 meters, so the x and y coordinates of 0.2 is going to be 30 in x and 30 in y to give a 45-degree angle. And L2 is 40 meters, so the x coordinate of 0.3 is going to be 40 plus 30 is 70, and the y coordinate of 0.3 is going to be 30. The beams have rectangular cross section of 10 by 10 or 10 centimeters by 10 centimeters, and the distributed load that is applied to this beam is 10 kilonewtons per meter, and the beam is fixed at this joint 1 and joint 3. So I have written a script in ANSYS APDL or for ANSYS APDL to solve for this problem. Let's go through step by step and see what it does. The first line finishes any undone work or any work that we have been doing so far. And this line clears database. Now we jump into pre-processing. Start pre-processing by using the prep7 command. Again, I have opened the ANSYS help file here so I can show you what each command does. So if I go to prep7 and the documentation says enter the model creation preprocessor. And it's always a good idea to have the help documentation open if you're new in writing APDL scripts, so you can refer to it for commands and information that you need. Now the fifth line in my code gives or selects the element type. So select beam 189 element type. Again, if I come to the element references here, and if I find element type 189 in the help documentation, I see that beam 189 and beam 188 are the ones that could solve for a beam problem. And as we said, frames are a mix of beams that are attached to each other. So I can use a beam 189 or beam 188 element type to solve this problem. I don't need to apply or define a real constant, so I can leave that blank. Now here I'm defining cross section of the beams, and it's a rectangle. Moving back to the command library of ANSYS APDL, I'm finding under S section type. Again, you run sec type command and then you give a reference number, which I've given 1 in here, and then you define the type, which I've said it's a beam. And beam has subcategories that you can see in here: rectangle. So if type is beam, we can have rectangle, quadrilateral, I-shaped, Z-shaped, and so on and so forth. So after I decide I want a beam, I have to define the type of the cross section. Now here, give cross section data for rectangular beam. So if I go back to section data and look for beams and the rectangular, so section data gets up to 12 values, and the first 4 values of section data for a rectangular beam are its width, height, and the number of divisions. By default, it's 2. I can change it, or I can leave it as default. But I need to determine the length, the width and the height of the rectangular beam. So I'm given 0.1 by 0.1, which means 10 to the minus 2 meters squared. Now here, I'm defining Young's modulus to be 210 gigapascals, and I'm defining Poisson ratio. So MP is short for material properties. You can find it here. MP, and then I have to give it label, which could be either of these values. If I find EX means elastic moduli, which is Young's modulus, and PRXY is the Poisson ratio. And then after that, I have to give the material model reference number, which I've given 1 to both of them. And then I give the values. I can give up to 4 values, but here I'm only giving 1 value for the Young's modulus and Poisson ratio, according to our model. Then I have to define the key points for my model. I need to define 3 key points. Again, if I go back to my PowerPoint, I have a point here, a point here, and a point here. We looked at the dimensions or x and y coordinates, so it's 30, 30, 70, 30. And point 1 is at 0, 0. So I have defined 3 key points. The first key point is at point 0, 0. If I load the K command, so it creates a key point. The first input is the reference number, so I've given 1. And the next 3 inputs are the x, y, z coordinates. So it creates a key point. A key point at x equals 0, y equals 0, z equals 0. Then I have to create 2 more key points. Now this one is at x equals 30 and y equals 30. So key point 2 is created at x 30, y 30, and z 0. Then I create a third key point at x 70 and y 30. So let's see what happens if I input these values in ANSYS so far. So I load ANSYS, paste the stuff there, and run it. I see that key point 1 is in here, key point 2 and key point 3 are created. Just for sanity check, let's take a look at the material model and element type. So beam 189 is defined for me. Then the material model 1 is created for me as I defined in my commands. And then I can look at the sections that I create for me. Plot sections, section 1, and this is a section. The area is 0.1. It also gives me the second moment of inertia about y and z axis. Now I have to use these key points to create lines. So L command creates key points between lines, or lines between key points. So L, P1, P2. And I can define the number of divisions or spacing, but for now I'll just leave it as blank. So I type L, and then I have to define the key point numbers, which refer to this, this, and this. So the first line is going to be between key point 1 and key point 2, and the second line is going to be between key point 2 and key point 3. So create a line between KP1 and 2, and then create an outline between key point 2 and key point 3. So I can select that and paste in here. If I do lplot, see that my lines are created for me. Next, I have to mesh this model the solid model to create my finite element model. And for that, I want to define an element size of 0.1. So set element size to 0.1. What that means is that all the elements that are created on the lines will be 0.1 meters in length. And I will show that to you after we mesh the model. Now here, set element type to reference 1, which is beam 189. So referring to this reference number, which is beam 189, set real constant to 1, which we don't have any real constant, so we can even skip this line. And here, set material model to 1. What that means is material model 1 that we defined there and in here are going to be used for meshing my lines. Now I'm going to create or mesh the lines. And LMesh, if I find it here, is short for meshing lines. LMesh, generate nodes and line elements along lines. And you can give the line numbers and increment of the line numbers as well. So let me just show you what that means. If I come here and if I click on numbers and say line numbers, I said I have two lines, line 1 and line 2, which I can use for meshing or referring to these lines. So here I could say LMesh all, or I could also say LMesh 1, 2 at every one increment. They both work. So if I give this value or these commands to ANSYS, I see that it creates elements for me. So if I do eplot, and I can also come here and say number the elements for me. So element numbering by color only for now. As you can see, very tiny elements have been created, which means my mesh is very fine. I could actually change the size of my elements, make them a little bit bigger. But for now, I'll just stick with what I have. Now I have to define the degrees of freedom. The node 1, which is located, or the first node which is located as 0, 0, 0, should be fixed in all directions. And the node located at x70, y30, and z0 should also be fixed in all directions. The D command applies a degree of freedom. So define a degree of freedom, and I can fix all of the structural degrees of freedom for the selected node. So node parenthesis x, y, z coordinate, all, and then the value. So fix 0.1. And then here, fix 0.3. If I copy these lines in ANSYS, I will see that this point and this point are fixed in my model. Now I'm selecting lines. So LCell is short for select a line. So if I come here, I can take a look at LCell, means select a line. And the second or the first input for that is S, means select a line instead of reselecting or also selecting or unselecting a certain line. And then I can define how I want to select a line, by which criteria. So here I'm saying by a line number, because I gave line as the input for the item. The next one, component, is not required because line number does not need a component. But then the third one, or the last one, is the line number. So again, if I go back to ANSYS and do lplot and show the plot or line numbers, do lplot again, didn't do that yet. So somehow it's not printing the line numbers, but we know that this one was my second line, or line number 2 from previously looking at the model. So, oh, I guess I know why it's not showing it, because it changed this to color only. Okay, now it should show it. So line 2 is here and line 1 is there. So I want to select line 2, and let's go step by step of seeing what it does. So LCell is short for select a line, and then I'm going to select only line 2. If I do that, put it in here and do lplot again, see that only the second line is selected for me. Now if I go back to my code, now I'm saying ncell ll means select lines that are select nodes that are attached to a line. So if I go there and find the nsll command, select nodes attached to a line, and I say select instead of unselecting or reselecting, and then I'd give 1, which means select both interior and end nodes. If I gave 0, it would only select the interior nodes, not the end nodes. So if I copy this line in ANSYS and put it in here and do nplot for plotting the nodes, see that my nodes are selected. Again, I have a very fine model here. I should probably have made my mesh a little bit coarser. So let me annotate my code before I move on. Select line 2, select all nodes attached to line 2, and now here I have ESLN, which means select elements attached to the nodes. So if I come to ESLN command here, ESLN means select the elements attached to nodes, and I'm again saying select instead of reselect or all select, and by 1 means I want to select all the nodes attached to the elements that have all the nodes attached to them. Next is applying the distributed load on the selected elements. So that's called SF beam because I'm applying that force to a beam. I can find SF beam here. First, I have to give the elements I want to apply the force to, and because I've selected my required elements so far, I can put all there. And then I have to give the load key, which is basically the direction of the force which is applied to the elements. 2 means in the y direction, so that's why I give 2 there. And then next is the label, which I'm saying pressure as the distributed load, and then the value is 10,000 newtons. So apply a 10 kilonewton distributed load to selected beam. And then here I'm selecting everything. And that's important because if you don't do this after selecting certain entities and I want to solve something in ANSYS, it will just crash and will not continue working. So let's put all these values or these commands to ANSYS and see what happens. And do eplot. Now I have the distributed load applied there, and my entire model is created. Now I can come here and say solve. So start solution and type, set analysis type to static, and then solve. So dash solu again starts the solution, nothing too specific about it, and then I can go to A and find the and type, should be here. You can define what kind of analysis you want to do, static, buckling, modal, or harmonic. You can just give it to and type, and then solve basically solves the model. So if I copy these lines and put them in ANSYS, you see that the solution is done. Now the next is doing some post-processing. So if I load the post one here, says enable database result post processor. So basically start post processing. And the first thing I'm doing here is to print reaction forces. So here PR is short for print, R is for reaction, and FOR is for force. So let's find it again here and see what ANSYS says about it. PRR4, I need to find that, which is in here. Prints constraint nodal reaction solution. And then here I'm setting select all the key points, or all the nodes attached to key points. I have 3 key points and I want to select all the nodes, select nodes attached to key points. So NSLK, N is short for node, SL is for select, and K is for key point. Select nodes attached to key points, and I can say select, reselect, also select, or uselect. Here I'm just selecting it. And for those nodes, I want to print nodal displacement, and then I want to print nodal rotation, and then select everything. So if I copy all of these commands and put them in ANSYS, I can see that the results are shown for me. So here I see the nodal rotations. So only node 2 has any rotation. Node 1 does not have any rotation. Then I can see the nodal displacements. Again, only node 2 has displacement, and X and Y, not in Z direction. And lastly, I can take a look at the reaction forces at node 1, which is here, and node 852, which is there. So Fx and Fy and Mz are non-zero values. These ones, 10 to the minus 11 and 10 to the minus 10, are basically zeros. We can also come here and say PL, which is short for plot, nodal solution, and sol is nodal solution, U, which is displacement, and say print or plot them in the Y direction. So this is how it deforms. Actually, this is exaggerated. If I come to the window, I can see that if I do it in true scale and find the Y displacement, it's actually a lot of displacement. I've applied a lot of force to my model. But so if I do auto calculate, this is how it would be. And then I can come here and plot controls, style, line size, and show the actual look of my model, which basically says why I'm getting a very big displacement, because my beams are very thin and the load that I've applied is very big. I want to turn that off. And I can take a look at the element stresses. Let's see what we get for X stress. Basically 58.7. And let's see if we can get von Mises stresses. So we learned how to solve a beam or a frame problem with distributed load using ANSYS APDL scripting in this video.